It's a great pleasure for me to introduce Francesco Pavese from Politecnico di Bari. He will talk about small complete caps and their relation with linear codes. So please.
Thank you, Ferdinando. And first of all, I would like to thank the organizer for this very important conference. And okay, in this talk, I will describe a class of combinatorial objects that are called caps. This is a joint work with Antonello Cossidente, Bense, Chaibok, and Giuseppe Marino. Let's start with some definition. Let Q be a prime power, and let V be an n-dimensional vector space over the finite field with Q elements. We will denote by PG R-1 R-1Q the projective space whose underlying vector space is V. And what is a cap in a finite projective space? Well, it is a set of points such that no three of them are collinear. And a cap is said to be complete if it is not contained in a larger cap. So in other words, this means that every point outside X lie on a line joining 2 points of X. And so this means that the definition of a complete cap is equivalent to the definition of another well-studied object in finite geometry that is one-saturating, that are the one-saturating sets. Complete caps provide instances of one-saturating sets. Vice versa is not true. There are examples of saturating sets that are not caps. In general, these objects are not only interesting from a combinatorial and geometric point of view, but they are very related, strictly related to linear codes. So let us briefly recall the important definition of a linear code. So the notation for a linear code is NKQ, which stands for a k-dimensional vector subspace of FQ to the n. Here, FQ to the n is equipped with the Hamming distance, and a very important parameter for a linear code is the minimum distance that will be denoted by D. Another important parameter is the error correcting capability of the code, which will be denoted by T, and the covering radius, which is the smallest positive integer, such that the balls centered at the code words of the code and having radius rho cover the whole space. And in general, one way to describe a code or its dual is by using a generator matrix or parity check matrix. Now, by regarding the representatives of points of a one-saturating set as columns of a parity check matrix, then a linear code is obtained having covering radius 2. And so this means that the minimum distance of a code arising in this way is at most 5. Moreover, we can think at the minimum distance as the smallest number of linearly dependent columns of the parity check matrix. But since every 3 points, every 3 columns have to be linearly independent by the property, if we consider X as a cap, then this means that for a cap, we have that the minimum distance is either 4 or 5. If the minimum distance is 5, then the code is said to be perfect. And actually, perfect codes have been classified, and they are so the property of being a perfect code translates in the geometric property such that no 4 points of the cap are in a plane. And this the only 2 caps satisfying this property are either the elliptic quadric in PG32 or the 11 complete cap of PG43. In the latter case, this cap arises by considering the action of a Mathieu group. So, besides these two sporadic examples, every linear code constructed from a complete cap gives rise to a quasi-perfect code. And so this means that there is a one-to-one correspondence between complete caps and quasi-perfect codes, except the two codes we have seen before. Another important parameter for a code is its covering density. That is always greater or equal than 1 and equals 1 in the case when the code is perfect. And in general, interesting codes have small covering density. So this point of view leads the important problem of finding the complete caps having small sides. So if we denote by T2 R minus 1Q the sides of the smallest complete cap in the corresponding projective space, then it is possible to provide a trivial lower bound simply by using counting arguments. So the natural question is if it is possible to construct small complete cap attaining the trivial lower bound. This problem has been studied by many mathematicians. In particular, in the plane case, Blockhaus, Ball, and Polverino provided an improvement on the lower bound when the field has either P or P square or P cube elements, respectively. As for the upper bound for the smallest sides, then in the plane case, there are constructions due to V2A Batangelo in the even characteristic case and Gabor-Korchmaros in the odd characteristic case. An improvement was obtained by Cerny, starting from the points of a cubic curve. And more recently, Kim and Wu, by using a probabilistic approach, provided a very, very good result. Here, D and C are independent from Q. So what about the problem in higher dimension? Well, Segre constructed a complete cap of these sides by using three conics sharing a point on three distinct planes and having the same nucleus by adding to the points of the three conics the nucleus, in the case when Q is even. So essentially, he solved the problem in this case. And let's mention that the analog problem in the odd characteristic case is still it has to be solved, since as far as I know, the for general Q, the smallest node cap has sides Q cube over 3 and was constructed by Faina and Pambianco. Pambianco and Storme generalized the construction due to Segre in projective space of odd dimension when the characteristic is even. And their construction was improved by Giulietti in 2006. So actually, these constructions say that it is possible to find small complete caps whose size is very close to the trivial lower bound in the cases when the ambient projective space has dimension odd and Q is even. The construction given by Giulietti was refined recently by Davidov, Giulietti, Marcugini, and Pambianco, and other construction were obtained by Davidoff and Ostergaard, Bartoli, Faini, Marcugini, and Pambianco in several papers. They also, Davidoff, Faini, Marcugini, and Pambianco also used a probabilistic approach in higher dimension. And very recently, Bartoli, Giulietti, Marino, and Polverino, by using the theory of linear sets, solved the problem in the case when the ambient projective space has even dimension and the field has an even square number of elements. For other techniques, we refer to the very nice survey written by Giulietti in 2013. Here, we would like to to outline a construction which of small caps which holds in odd characteristic for field of odd characteristic as well. In the case when the ambient projective space has dimension congruent to -1 modulo 4. In order to do that, we consider a vector subspace, a vector FQ space with vectors represented by elements in this way. And so we consider, let's say, a non-standard representation of the ambient projective space. Here, it is very easy to recognize a partition of the points of the projective space into two disjoint 2n dimensional projective space and certain point sets V omega having the same size as pi1 and pi2. This partition is left invariant by a cyclic group having the same order as the number of points of pi1 and acting semi-regularly on points of the projective space. And actually, the complete cap arises by selecting in a suitable way two of the point sets V omega, let's say V1 and V alpha. So the size of the complete cap is very close to the trivial lower bound. And in order to see that it is a cap, it is possible to use the group, and hence we can pick an arbitrary point on V alpha and prove that no 2 points of V1 are collinear with V alpha. This is equivalent to say that for every lambda and rho in FQ, this system of equation admits no solution in X and Y. In order to see the completeness, we can use the partition of the points of the projective space and the group. This allows us to take a point outside of this type, 1 omega, and see that there are 2 points, a point of V1 and a point of V alpha, such that the chosen point is collinear with them. This problem translates into the fact that there exists lambda and rho in FQ, such that this system of equation has a solution for every omega. Actually, to solve this algebraic problem turned out to be very difficult, quite difficult in the case when Q is odd and omega squared minus 1 is not a square in this field. It translated into the problem of finding a non-zero root of this linearized polynomial. That could be done by invoking a result due to Osbudak that ensure us the existence of such a root simply by looking at the existence of a root in the quadratic extension. So we can provide also a geometric description of this construction, and this can be done by considering a projective space whose underlying vector space consists of symmetric matrices having this shape. In this way, it is quite natural to determine n+1 pairwise disjoint 2n-dimensional projective spaces. And again, it is possible to see that outside the span of at most n of these n+1 pairwise disjoint spaces, every point of the ambient projective space lie on a Veronese variety. So we have these sets of Veronese varieties that provide a partition of the points of the ambient projective space outside the span of at most n of the pairwise disjoint 2n-dimensional projective spaces. Now, if we project two suitable Veronese varieties from n-1 of the n+1 2n-dimensional projective space onto the span of the remaining two, then we get exactly the cap we have seen before. So we are saying nothing else that the cap we have constructed are union of two projections of Veronese varieties. Okay, that's all I wanted to say. Thank you for your attention.